Hey guys, welcome back to another video. In today's video, I'm going to be talking about Rolle's theorem and the mean value theorem. So let's begin. Rolle's theorem states if a function f of x is continuous on a closed interval a to b, differentiable on the open interval a b, and if f of a is equal to f of b, then there exists at least one number c in ab such that the derivative at c is equal to 0. So let's say we have a graph like this, and it goes, nope. Okay, so let's say we have a graph like this, and it goes from here to here. No matter what happens, you have to reach the same point somehow. But in order to do that, the derivative has to equal 0 at some point. Because you're either decreasing and then increasing, or increasing and then decreasing. But the derivative has to switch signs at some point, or approach 0 to get back to its original starting point. So to apply Rolle's theorem, make sure that the function is continuous for all points in AB, the function is differentiable for all points in AB, and that f of a is equal to f of b. If all three conditions are met, then there exists at least one number c in AB such that the derivative at c is equal to 0. So using these guidelines, we're going to verify that the Rolle's theorem applies for f of x is equal to x squared minus 4x plus 4 on 0 to 4, or the interval 0 to 4. So this is going to be our left boundary over here and our right boundary over here. So the first thing we're going to do is check if it's continuous for all points in AB. So this is just a polynomial. All polynomials are continuous for its entire domain. So this can be checked off. And now the second one states the function is differentiable from all points in AB. Every polynomial is differentiable. And now we have to check that f of a is equal to f of b. So f of 0 is equal to 4. Or if we plug it into here, it's 0 minus 0 plus 4 is equal to 4. And now let's see if f of 4 is equal to f of 0. F of 4 is equal to 16 minus 4 times 4, or just negative 16. So these cancel out. Plus 4 will be equal to 4. So yes, they do equal, and Rolle's theorem does apply here. So what we do next is take the derivative of the original function. So we get that f prime of x is equal to 2x minus 4, and we want f prime of c to equal to 0. So we're looking for some value where 2c minus 4 is equal to 0. Add 4 to both sides. We get that 2c is equal to 4, and that c is equal to 2. And we get that our answer is c is equal to 2. So the derivative at 2 is equal to 0, and this can be shown with the graph as the as the tangent line is horizontal here. Okay, so now let's talk about the mean value theorem. If a function f of x is continuous on the closed interval a to b and is differentiable on the open interval a to b, then there must exist at least one number c in the interval ab such that the derivative of the function at c is equal to f of b minus f of a over b minus a, or that's equal to the change in y over change in x of that function from a to b. So in other words, the derivative at c equals the average or mean rate of change over ab, and there exists a point on the interval where the slope of the secant line from the endpoints equals the slope of the tangent line. So you have some graph like this, and you have a point A over here and a point B over here. So this is the x value for B and the x value for A. So at some point here, there's a secant line that goes through them, but somewhere on the line that passes through here, there's a tangent line that's parallel or has the same slope as the secant line between these 2 points. So to apply the mean value theorem, make sure that the function is continuous from all points in AB and is differentiable from all points in the open interval AB. So now we're going to find all of the values of c in the interval 1 through 4 such that the mean value theorem applies for f of x is equal to x squared. So the mean value theorem is f prime of c is equal to f of b minus f of a over b minus a. So this can be replaced with the things that were given for the question. So now we have f of 4 minus f of 1 over 4 minus 1. If we were to plug everything in, f of 4 would be 16, and f of 1 would be 1. 4 minus 1. So now we have 15 over 3, and we get that the slope is equal to 5. So we want to find some value for c such that the derivative is equal to 5. So let's find f prime of x. F prime of x is just equal to 2x, because the derivative of x squared is 2x. So now we're going to find f prime of c, which is equal to 2c, which is equal to 5. So we get that c is equal to 5 over 2. So if we were to draw the secant line from here, it would look something like this. Okay, and at x equals 5 over 2, so that's 2.5 around here, the tangent line will be parallel to the secant line. It can't really be seen here because of the width of the pen, but those two lines are parallel to each other. Okay, so now let's do some practice problems. We're going to determine whether Rolle's theorem applies to the function on some interval, and if it does apply, we're going to find all the values of c, where f prime of c equals to 0. So the first test we're going to do, if it's continuous for all points inside of AB, absolute value function is always continuous. So this first condition can be checked off. The second condition asks, the function is differentiable for all points in AB. So for an absolute value function, the only point where it's not differentiable is when the absolute value is equal to 0, because there are going to be two different slopes at that one point, which means that the derivative will not exist at x equals 2. But as you can see here, 2 is within the interval, which means that Rolle's theorem does not apply because this condition is not met. So no, does not apply. Okay, so now we're going to do the same thing for the function f of x is equal to x squared minus 4x plus 4 on 0 to 4. So the first condition is to check if it's continuous. All polynomials are continuous on their entire domain. So this one can be checked off. The function is differentiable. Every polynomial is differentiable. And we're going to check if f of a is equal to f of b. So f of a, or f of 0, is equal to 0 minus 4 plus 4, so you get 4. F of 4 is equal to 16 minus 4 times 4 plus 4. So now we get 0 plus 4 is equal to 4, and they are equal to each other, which means that the third condition is met. So we're going to find f prime of c, so that's equal to 0 within that interval. So we're going to differentiate f of x, so we have 2x minus 4, and we're going to find f prime of c is equal to 0 is equal to 2c minus 4. 4 is equal to 2c. We get that c is equal to 2. So f prime of 2 is equal to 0. Okay, so now we're going to do the same thing, but for x squared plus x minus 2 from -2 to 1. So this function is continuous on the interval, and it's differentiable on that interval. So now we're going to find f of a, so f of -2, that's 4 minus 2 minus 2, and that's equal to 0. F of 1 is equal to 1 plus 1 minus 2, which is also equal to 0, so all three conditions are met. So we're going to differentiate the function, so f prime of x is equal to 2x plus 1, f prime of c is equal to 0, and it's equal to 2c plus 1. The reason why we change x into c is because we're essentially plugging in c in the place of x. So what we're going to do is solve for c. So you get 2c is equal to -1, and that c is equal to -1/2. And that's going to be our final answer. So now we're going to see if Rolle's theorem applies to the function x cubed minus 27 over x minus 3 from the interval -6 to 3. So our first check is to make sure that it's continuous on the entire interval. So if you were to plug in 3, you would obviously get 0 in the denominator, which is undefined. So let's check for continuous. So now let's check if it. So first, let's check if it's continuous. As you can see here, there's a term in the denominator, but when the x is equal to 3, the denominator becomes 0. But 3 is an endpoint here, which means that f of 3 is equal to 3 squared 27 minus 27, 3 minus 3, or 0 over 0, which is undefined, which means that f of x is not continuous for the entire interval, which means that Rolle's theorem fails. So no, it does not apply here. Okay, so now we have the same function, but this time with a different interval. So we're going to do the same things to check for the conditions. So this function is continuous from -3 to 0 because there's no undefined values throughout here. So the first condition can be checked. This function is differentiable for the entire interval using quotient rule, which means that the second condition is checked off. But now we need to make sure that f of -3 is equal to f of 0. So let's plug in f of -3. F of -3 will be -27 minus 27 all over -3 minus 3. So we get -54 over -6. These turn positive. And we get that f of -3 is equal to 9. So now let's find f of 0. F of 0 would be -27 over -3. This turns positive. And now we have that. This is 9. So these two are equal, which means that the theorem does apply. So now we're going to find when f prime of c is equal to 0. So we're going to differentiate. So f prime of x is equal to x minus 3 multiplied by 3x squared minus x cubed minus 27 multiplied by 1 all over x minus 3 squared. So what I'm going to do is factor out an x minus 3 term from here and divide. So now I have f prime of x is equal to x minus 3 multiplied by 3x squared minus x minus 3 x squared plus 3x plus 9. This is using the same opposite something always positive formula, which can be used to factor out difference of cubes or sum of cubes. So this is just a sum of cubes formula. And I'm going to divide by x minus 3 multiplied by x minus 3. So one of these can cancel out. So I'm going to make some room here. So now we're left with this. And what I'm going to do is simplify. So now we get that f prime of x is equal to 2x squared minus 3x minus 9 all over x minus 3. So now what I'm going to do is factor stuff out. So these two multiply to -18. The factors of negative 18 that add up to -3 will be -6 and +3. So I'm going to put 2 x plus 3 multiplied by x minus 3, and that will be our factor out terms. And we can divide by the denominator once again. And now we have that f prime of x is equal to 2x plus 3. We want to find it when it's equal to 0. So f prime of c is equal to 0, is equal to 2x plus 3. And when we solve for, okay, so now we're going to apply the mean value theorem to f of x is equal to x squared on the interval 1 to 3 and find all values of c in 1 to 3 such that the mean value theorem applies, basically. Such as like the secant line is equal to some tangent line. Some points tangent. Okay. Okay, so now we're going to apply the mean value theorem to find f of x is equal to x squared. Okay, so now we're going to apply the mean value theorem to f of x is equal to x squared on the okay, so now we're going to apply the mean value theorem to f of x is equal to x squared on the closed interval 1 to 3 and find all values of c in the open interval 1 to 3 such that the derivative at some point c is equal to the secant line between the two endpoints. So we need to make sure that the function is continuous. It is. And we need to make sure that the function is differentiable, which it is. So now let's find the secant line. So f of 3 will be 9, f of 1 will be 1, 3 minus 1 is equal to 2, so we get that 8 over 2 is equal to 4. So we need to find some value for c that's equal to 4. So we're going to take the derivative, and that's equal to 2x. So we're going to find f prime of c, that's equal to 2c, which is equal to 4. So once we solve for c, we get that c is equal to 2. Okay, so now we're going to do the same thing, but for x cubed on the closed interval 0 to 2. So we're going to solve for the secant line. So we're going to start with the right endpoint. F of 2 will be 8. F of 0 will be 0. All over 2 minus 0, which should just be 4. So now we're going to take the derivative. And we get that the derivative is equal to 3x squared. And we get that f prime of c is equal to 3c squared. And that's equal to 4. So now when we solve for c, we get that c squared is equal to 4 over 3. And that c is equal to the square root of 4 over 3, or 2 over square root of 3, or if you rationalize it, 2 square root of 3 over 3. And that's our final. Okay, so now we're going to do the same thing, but for the function 1 over x on the interval 1 to 4. So let's apply the mean value theorem. So f prime of c is equal to f of 4 minus f of 1 all over 4 minus 1. So we get that f of 4 is 1 over 4. And then we subtract f of 1, which is just 1, all over 4 minus 1, which is 3. Okay, so what I'm going to do now is multiply both sides by 4 on the bottom and on the denominator, so I can get rid of the fraction. So now I have 1 minus 4 over 12. And now we have the slope is negative 3 over 12, which will lead to negative 1 over 4. We're going to find f prime of c such that it equals to negative 1 over 4. But first we need to take the derivative of the function. So we're going to find d dx of x to the power negative 1. Using power rule, we get that's equal to negative x squared. Negative x to the power of negative 2, or just negative 1 over x squared. So now we have negative 1 over c squared is equal to negative 1 over 4. They both have negative symbols, so they can turn positive now. And now we have that 1 is equal to c squared over 4, and that 4 is equal to c squared, and that c is equal to 2. It's not negative 2, because negative 2 is outside of the interval, which means that positive 2 is the only one that applies inside of here, which will leave us with our final answer, c equals 2. Okay, so now this problem says a ball rolls around a straight track with position function f of x is equal to x squared minus 6x plus 8 on the closed interval 2 to 6. So we're going to find the slope of the secant line from 2 to 6. So we have f of 6 minus f of 2 over 6 minus 2, and f of 6, which will be 36 minus 36 plus 8, So we got this is equal to 8. F of 2 is 4 minus 12 plus 8, and that cancels out to be 0. And 6 minus 2 is equal to 4, and we got that the slope of the secant line will be equal to 2. So that's the answer to part A. So we're going to use the mean value theorem to find the values of C where the instantaneous rate of change is equal to the secant slope. So what I can do here is just add on f prime of C. So f prime of C is equal to 2. So we're going to differentiate the original function f of x. F of x is equal to 2x minus 6. F prime of C is equal to 2, which is equal to 2c minus 6. I'm going to add both sides by 6. So we have that 8 is equal to 2c, and that c is equal to 4. So when c is equal to 4, that's when the instantaneous rate of change is equal to the secant slope. Okay, so this is going to be the first part of the last problem. So this says that a highway patrol monitors a car traveling along a 210 mile long road. The car leaves City A at 8 a.m., traveling at 60 miles per hour, and arrives at City B at 11 a.m., traveling at 60 miles per hour. The speed limit on the road is 60 miles per hour. So this is asking us to find the average velocity of the car during the trip. So we have V average is equal to F of, I'm going to put S of 3 minus S of 0 over 3 minus 0. The reason I put S, because S will be our position function, and 3 will be how much hours we go from the beginning. So let's say 8 a.m. is when time is equal to 0, and that 11 a.m. is when time is equal to 3. So when we reach the end after 3 hours, we're going to be at 210 miles away. At the beginning, we just started traveling, so we're at 0 miles, and 3 minus 0 is going to be equal to 70 miles per hour, which will be our answer to the first part. Okay, so now we are going to use the mean value theorem to prove that the car must have exceeded 60 miles per hour at some point during the 3-hour interval or journey. So we know that the velocity average is equal to 70 miles per hour, and that's equal to S of 3 minus S of 0. And as you can recall from the mean value theorem, this is the same thing as S prime of C. So at some point in the interval 0 to 3, there's a C such that it's equal to 70 miles per hour. So because of that, there's some point that the velocity of the car is higher than 60 miles per hour because it has to be 70 miles per hour at some point. Thank you for watching this video. I hope you enjoyed, and stay tuned for more. Goodbye.